Welcome to CE1 Group 2 video presentation on the Integrated Design project for the September 2020 semester. In this video presentation, we will elaborate briefly on the findings that we have obtained for all 4 chapters. These are the group members for Group 2, and these will be the contents of the video presentation. I will proceed next with Chapter 1.
Welcome to Chapter 1 of our Integrated Design project. In this chapter, I'm going to talk about the introduction of methanol and its production process. Methanol, which is also known as CH3OH, is the simplest form of alcohol consisting a methyl group attached to a hydroxyl group. Some of the general characteristics of this substance are volatile, colorless, and it produces a mildly sweet pungent odor similar to ethyl alcohol. The most used and known procedure of synthesizing methanol is through natural gases, as it is economical. Steam methane reformer is one way to produce methanol from natural gases, where these natural gases with steam is sent as feed to the reformer, then yield carbon monoxide, carbon dioxide, and nitrogen, which will undergo methanol synthesis, which will produce methanol. In the methanol production, natural gases are the most abundant source and popular as feedstock because of its economical properties. However, there are also other feedstocks that can be used. For example, coal, which has been increasingly popular as feedstocks for methanol production, particularly in China. Moving on to the methanol market analysis. Methanol application cover a vast sector and industry but can be generally divided into two groups, which is chemical and fuel transportation sector. Being the most dominant regional market for methanol, Asia Pacific is the largest producer and consumer of this product, with more than half of global production and about 65% of world demand, followed by Middle East and Africa. In terms of production, the global market for methanol is segmented into three derivatives of methanol, which are acetic acid, formaldehyde, and dimethyl ether. Tremendous growth in automotive sector and growing demand for chemical intermediates across the globe seem to be the key drivers for methanol markets. With depleting crude oil reserve over a recent year, the demand for alternative transportation fuel has triggered the market for methanol. Due to these reasons, it is economically feasible in terms of the plant operation, since the production line is expected to contribute to the demand for numerous derivatives. And to the methanol synthesis and methanol production process, most of the hydrogen generated is produced by steam methane reforming, a mutual production process in which hydrogen from a methane supply, such as natural gas, is produced by high temperature steam, which are normally in the range of 700 degrees Celsius to 1000 degrees Celsius. In steam methane reforming, in the presence of a catalyst to create hydrogen, carbon monoxide, and a relatively small volume of carbon dioxide, methane reacts with steam under 3 to 25 bar pressure. Steam reforming is endothermic, which means that the mechanism for the reaction to continue must be supplied with heat. Methanol synthesis, the makeup synthesis gas and the recycle contains mostly hydrogen, carbon monoxide, and carbon dioxide. The three main reactions for the methanol formation include hydrogenation of carbon monoxide, hydrogenation of carbon dioxide, and then coupled with the reverse water-gas shift reaction.
Chapter 2, we start first with finding the mass flow rate for each stream to perform mass balance. According to a literature review that has been done, the approximate plant capacity of methanol synthesis is 2,500 tons per day, in which when converted to kilogram per hour gives the value of 94,498.4 kilogram per hour. The value is then used to determine the mass flow rate for stream 10, 11, 12 at the boundary of methanol purification unit. At the syngas recovery unit, mass flow rate for streams 6, 7, 8, and 9 are obtained. The composition of component in stream 8 is also obtained. At the condenser and methanol reactor unit, the mass flow rate for stream 3, 4, 5, and the composition of component at stream 5 is also obtained. At the reforming reactor unit, by using the extent of reaction method, mass flow rate for stream 1 and 2 is obtained. As a result, the mass flow rates of each stream are obtained to be as in the table given. When checking the validity of the value, or when checking the mass balance, it is obtained that the percentage error is 0%, indicating that the mass balance that has been performed is correct. The process flow diagram for methanol synthesis are obtained as shown. The process of methanol synthesis starts with water and methane mixed together in the mixer, as the production of syngas is obtained through the reaction of methane under excess steam. At the reforming reactor R101, through steam methane reforming and at given condition, syngas is produced. The chemical reaction is as shown. The syngas is then fed into the condenser D101 to remove excess water. The remaining product then enters the methanol reactor R102, where the reaction is as shown. When the product of the methanol reactor leaves, the excess syngas and methanol are fed into syngas recovery unit D102, where CO and H2 are recovered and purged out from splitter at stream 9, and the remaining is recycled back into R102 through stream 8. And lastly, the bottom product of D102 is then further purified at methanol purification unit D103 with operating conditions as given.
Chapter 3, Part A. The temperature at S10 is 52 degrees Celsius. In the HiC software, component used in S10, methanol and water is added to the component list. After choosing the suitable fluid package, the vapor-liquid equilibrium graph from the binary mixture of methanol and water are generated. The XY diagram, the blue curve is the XY curve, while the red line is the reference line with slope 1. XY and PXY diagram, the blue line is the bubble curve, while the red line is the view curve. Online available experimental data of VLE at temperature of 49.76 degrees Celsius was obtained from Dormant Data Bank DDB website. Data was chosen for comparison with the generated data we obtained from HiCs, because the temperature used in this data is the nearest to the temperature we use in HiCs. All the VLE graph from HiC software have the same pattern with the one from DDB experimental data, although they are not identical. As such, the result of the experimental data is acceptable for comparison, although it is not identical with the generated result from HiCs, because the result from the software have systematic and random error that might occur during the experiment, but are not considered. Then we are required to construct the phase envelope of mixture in D103 using the following condition of temperature is equal to 52 degrees Celsius, mass fraction of methanol equal to 0.9264 and mass fraction of water 0.0736. So this is the PV diagram, PS diagram, PP diagram, and PH diagram of phase envelope diagram. This is the TV diagram, PS diagram, and PH diagram of phase envelope. Let's see. So this is the flow diagram that we simulated in HiCs. 155 for using 950 degrees Celsius and 2000 kilopascal for pressure and temperature. We found a reference online that stated that in steam methane reforming, methane reacts with high temperature steam 700 degrees Celsius to 1000 degrees Celsius under 3 to 25 bar pressure, which is equivalent to 300 to 2500 kilopascal. We assume that it is 10,000 kg per hour. Part C, we are required to predict the mole fraction of vapor over liquid. The mole fraction of vapor is 0.8909, the fraction of liquid is 0.1091. Therefore, we get a mole fraction of vapor over liquid, which is 8.1659. Then we are required to find the vapor composition and the liquid composition using flash calculation. S5 we can obtain the vapor composition, and from S4 we can obtain the liquid composition.
Next, we go to chapter 4, separation process 1. In this chapter, we are required to design the distillation column for the methanol purification unit and also to determine the number of theoretical stages needed. So first, a set of assumption is made, and the highlight of the assumption is that the condition given for S10 temperature is 52 degrees Celsius, and the fraction of the feed to the methanol purification unit S10 that is vaporized in distillate S11 is 0.96. By referring to this diagram, we can see that there are three streams connected to this distillation column, S10, S11, and S12. Taking value from chapter 3, we can calculate the amount of feed that enter in each stream, and by assuming the basis of 100 gram, you can calculate the composition of component A and component B in each stream. A graphical method is used to determine the number of theoretical stages, And firstly, by using end-to-end equation, we can find the saturation pressure for component A and component B. And through these two information, we can calculate alpha, where alpha is being used to generate an equation for the equilibrium curve. It also generates a table of XA and YA. After drawing the equilibrium curve on the graph, we need to find the Q line, and to do so, we substitute 0.96 into this equation, and then we got the Q value, and then we substitute the Q value into this equation to find the equation for the Q line, and then we draw the Q line onto the graph. The intersection of the Q line and the equilibrium curve will give us the value of x prime and also y prime, which later being used to find the minimum refractive ratio through this equation. It is stated that the optimum value of refractive ratio is between 1.2 R minimum to 1.5 R minimum. So by doing that, we're going to do a two set of trial using two different values of refractive ratio. For the first trial, we're going to use 1.2 R minimum, which give us value of 0.156. After we got the R value, we substitute it into this equation, and then we have the equation for the enriching operating line here. After that, we can calculate the number of the trace needed by stepping down through the graph until it passes the point XW here. So on the one, we got 3.1 plus 1 reboiler. By using the exactly same step as the trial one, we're gonna replace the value of R with 1.5 R minimum, which gives us a value of 0.195, and then we substitute the value of R into this equation, and then we draw it onto the graph, and then we repeat the step to find the number of theoretical stages. For this set of trial, we got 2.4 and plus 1 reboiler. On the comparison made between these two trials with different value of refractive ratio, we can conclude that distillation column from trial 2 is better because it requires lesser number of trays, which is more cost efficient. There are no 2.4 tray. We conclude that the number of trays needed is 3 plus 1 reboiler. We also determine that the number of feet entering the distillation column is at tray number 1.
That's all from us. Thank you.